Hi again everyone, Chris Tisdale here again. In this presentation I'm going to start a new series of videos on complex numbers. In particular, the assumed knowledge for this series of videos is virtually no acquaintance or understanding with complex numbers. So I'm going to assume that you're totally new to complex numbers and you want to learn about them. Now in this presentation I'm going to tell you why complex numbers are awesome. So I'm going to motivate the idea of complex numbers. I'm going to talk about a few examples where they have interesting applications, and I'm going to, basically define a form of a complex number and discuss how to represent them graphically. But the main focus is on motivating the subject and giving you some interesting angles and applications with complex numbers. So let me share my screen with you, and we can get underway. All right, so this is going to be a gentle introduction to complex numbers, and I'm not assuming you know anything about a complex number. All right, so where are we going? We're going to learn about a new kind of number called a complex number, and we're going to discover the basic properties of complex numbers and look at some of their applications. Now, the fundamental thing that the idea of a complex number is built on is this idea of an imaginary unit, which we denote by I. Now, this I is defined as the square root of -1. Now, at high school, you're always told, oh, you can't take the square root of a negative number. Well, you can, and we denote I as I guess, the positive square root of -1. And if that's the case, then I squared will equal -1. So this is the strange situation where you square a number, or you square this imaginary unit, and you get a negative number. Now, that may seem crazy, but it turns out that it's a really useful idea, both mathematically and for applications. Okay. Now, let me just talk a little bit about why complex numbers are absolutely awesome and worth learning about. There are two reasons. The first is their applications to the world around us, and sometimes these seemingly abstract and almost esoteric roots of negative numbers turn up in all sorts of applications. And secondly, complex numbers gives us the ability to simplify mathematics. Okay, now people see the term complex numbers and they go, oh, complex, that might mean it's really complicated and complex. Well, no, the idea with complex numbers is to make life and mathematics simpler. Okay, not make it more difficult. We want to simplify it. And complex numbers can do this. Let me give you some examples. This imaginary unit I arises in the solutions to a very famous differential equation called a spring mass differential equation. So for example, imagine this is like some wall or roof or something, and you attach a spring to that, and then you attach a mass, okay? And you push the mass up, or you pull the mass down and you let it go. That spring mass system will vibrate up and down. And Newton's second law leads to this kind of differential equation. Here, x is a function of time, then it's the position of the mass at time t from its equilibrium point. M is the mass, k is the spring constant. Large value of k means a strong or stiff spring. And you can show that these two functions, okay, if you look at them closely, they're basically exponential functions with an I and a square root and the variable t in them. These two functions satisfy this spring mass equation. How would you check that? You would differentiate this twice, treating I as a constant, okay, and plugging it in here and showing that this holds. Same with this one, okay? So you differentiate this with respect to t, imagine I as a constant, and you would plug it in here. So that's one way, one place where complex numbers appear, okay, in the study of vibrations and vibrating systems. Secondly, the imaginary unit also appears in transform techniques, and in particular in Fourier transform techniques. And transform techniques are important for solving differential equations from science and engineering. So these are a couple of examples where this imaginary unit and complex numbers pop up in applications. Now, let's look at the second part here. I'm claiming that complex numbers have the ability to simplify mathematics. Well, what do I mean by that? Well, complex numbers provide a simpler framework from which we can view and do mathematics. Okay, well, as a result, methods involving these complex numbers can simplify calculations, and in particular, if you use complex numbers, it can remove a lot of the boring and tedious parts of mathematical work. Let me give you some examples. Okay, suppose I've got this indefinite integral here. Okay, so I want to integrate e to the negative t times cosine t with respect to t. Now, if you look at that and you're familiar with, say, a first course in calculus, you'd go, oh yeah, I just integrate this by parts. Well, you'd integrate this by parts, sure. You'd actually have to do it twice. And you know, it's not a quick process. But if you use complex numbers to perform this integral, then many people think that this is actually a far more efficient way to compute this integral. Now, I'm not going to show you how to do that now, but I'm just saying that complex numbers provide a quick alternative to integration by parts for something like this. So complex numbers can save you time. Secondly, complex numbers are great at deriving trig formulae. Okay, now sometimes I forget these trig formulae. I can't remember every trig formula, but I can derive them. And in particular, you can derive trig formula using complex numbers. So the important thing here is that you may never have to remember another trig formula ever again. If you have a good understanding of complex numbers, they provide the framework from which you can derive many, many, many trig formulae. So again, it provides a way of deriving and simplifying these things associated with the trig formulae. Okay. Now, I've motivated the study, hopefully. Complex numbers are awesome because of their applications and their ability to make mathematics simpler. That's the idea. So this begs the question, what is a complex number? Well, I showed you this imaginary unit, I, over here, where I would say the positive square root of -1 and I squared equals -1. But we can go a little bit further than that. Here are some examples of complex numbers. Okay, so you can see in each of these expressions, you've got the imaginary unit. In some cases, you've got a real number added in, and here you've got a 2i, so you've got 2 times the imaginary unit, 3 times the imaginary unit, -1 times the imaginary unit, and so on. Okay, so as a general form, the Cartesian form of a complex number z, we usually use the letter z to denote a complex number, is in this form. X plus yi or x plus iy. Okay, some books have it this way, some books have it this way. Okay, up here I've got it x plus yi, where both x and y are real numbers. Okay, and I is the imaginary unit. Now, the x part is called the real part of the complex number z, and the y part is called the imaginary part of the complex number z. So let me go up here and show you what's going on. So the real part of, say, 3 plus 2i, all right, so this RE stands for the real part of what's here, would just be 3. And the imaginary part of 3 plus 2i would be not 2i, but just 2. It's just the sort of the coefficient of i, okay, according to this definition. So these parts are still real numbers, but they're just covered here in this definition. Okay, if I was to do this one, the real part of 2i, well, that's just the real part of 0 plus 2i, so the real part's 0. And the imaginary part of 2i is not 2i, it's just 2. Okay, and let's do this one. Oh, actually, let's do this one up here. The real part of -7 plus 3i is -7, and the imaginary part is just 3. Okay. All right, we'll use the real parts and the imaginary parts of complex numbers in forthcoming presentations. Here are some examples of complex numbers. This is the general Cartesian form. How do we express a complex number graphically? Well, we have a plane from which to do so, called the the complex plane. Let me draw a picture and I'll show you. Okay, so this complex plane has two axes, a horizontal one and a vertical one. Whoops. Okay, a bit sloppy there, sorry about that. Now the horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. Okay, so if I look at these, some of these complex numbers from before, okay, and I wanted to plot those, let's look at, say, 3 plus 2i. Okay, so along the horizontal axis, you just have real numbers, and along the vertical axis, you have, say, I, 2i, 3i, 4i, negative I, negative 2i, negative 3i, etc. Okay, so if I wanted to, say, plot 3 plus 2i, I would go 3 units to the right and 2 units up. Okay. If I wanted to plot, say, -7, -7 plus 3i, I'd go -7 this way and 3 units this way. Okay, what happens if I wanted to plot 2i, let's say? Well, I'd go 0 units. I just basically stay on the vertical axis and go 2 units up to 2i. Okay. If I wanted to plot, say, -2 minus 2i, I'd go 2 units to the left and 2 units down. Okay. And if I wanted to plot, say, negative 6 minus I, I'd go 6 units there and 1 unit down. Okay, now I can also plot real numbers. If I wanted to plot the number 3, I would just go over here. Okay, I'm not moving up or down the imaginary axis or the vertical axis. I'm just staying on the real axis. So all the real numbers lie on the real axis. Okay, so that is a brief introduction and motivation to complex numbers. They're important because, first of all, they make mathematics simpler rather than complicating it, and they also find really nice applications. I've told you what a Cartesian form of a complex number is and how to locate them or plot them on the complex plane, sometimes known as an Argand diagram. Okay, in forthcoming videos, I'm going to talk about basic operations with complex numbers: addition, subtraction, multiplication, and division. So I hope you can join me for that presentation. If you have any comments, any questions, you can put them in the comment section below. Thanks for watching. See you soon. Bye.